This is the second lecture from Chapter 16, and this one focuses on how we determine the strength of an acid or a base. And you will learn there are what we term strong acids and bases and weak acids and bases. The definition of a strong acid is that it donates all of its acidic hydrogen ions. So, for example, if you have hydrochloric acid, which is a strong acid, when you put it into water, it will 100% ionize or 100% dissociate into the hydrogen ion and the accompanied anion. It's also, all strong acids are strong electrolytes. Now, just to kind of prompt your memory, the definition for electrolyte is something that conducts electricity. And in order for a substance to conduct electricity, it must have freely moving ions. And since a strong acid completely dissociates into the ions, it is also a strong electrolyte. And once again, due to the fact that it's a strong acid, the concentration of the original acid equals the concentration of hydronium ions. And that's because all of this acid ionizes. So it's real easy to calculate pH. All right, so there are only 6 strong acids, believe it or not. There are only 6 acids we know of that dissociate 100% in water, so you simply have to memorize them. And every other acid known is considered a weak acid. Similar story for bases. A strong base is something that completely ionizes or dissociates. If it's a hydroxide base, that is dissociates into its cation and the hydroxide. And again, because you have all these freely moving ions, a strong base is also a strong electrolyte. And the strong bases to memorize are all of the hydroxides that are accompanied from a group 1 metal. So that would be lithium, sodium, potassium, etc. And only the heavier group 2 hydroxides. So if you're looking at the periodic table in group 2, only the metals at the bottom make strong base hydroxide. So that would be strontium and barium hydroxides. Alrighty, so just to look at a weak acid still donates a hydrogen ion, but just not as many of them. So an example of a weak acid would be hydrofluoric acid. When you put it into water, instead of it 100% dissociating into the ions, in this case it'd be fluoride and hydronium ion, only a certain portion of the HF molecules would dissociate, but the vast majority of them will remain intact just as HF. The most important implication of this is that the concentration of hydronium ion, remember that's how we calculate pH, so the concentration of hydronium ion for a weak acid is not equal to the concentration of the original acid. Okay? It's going to be a lot less because remember most of this original acid does not turn into the hydronium ion. That's when things get complicated toward the end of this chapter. How do we quantify the strength of an acid or a base? We don't do it with pH because pH tells us about concentration, but it really doesn't tell us about the inherent strength of the acid or base. So what we use to tell us about the strength is the equilibrium constant. We call them Ka for acids and Kb for bases. Now they're determined the exact same way we determine any equilibrium constant. So it's products over reactants. And if there were coefficients in the balanced reaction, those coefficients would be exponents. The larger the equilibrium constant, the stronger the acid or base. So I would jot that down. That makes sense, right? The larger Ka is, for example, the more hydronium ion you have, and therefore the more acidic it is. So what about the structure makes an acid a strong acid or a weak acid? The strength of an acid depends on two things. One, on the strength of the bond between the hydrogen and the atom it's attached to. So obviously the stronger that bond, the less acidic. You think about that. If that bond between hydrogen and the electronegative atom it's attached to is strong, it's not going to want to break and let go of the hydrogen ion. Okay? So the strength of the bond is important, and the stability of the resultant anion. So once an acid gives away a hydrogen ion, it's left with an anion. The more stable that anion is, the more likely it is to form. Okay? So the more stable the anion is, the more acidic the original acid is. So that's kind of an explanation, but what you need to commit to memory is that as you move to the right across the periodic table, we know that electronegativity increases, right? Well, it also turns out that acid strength increases going from left to right. And that's because electronegativity of the atoms that hydrogen would be attached to is also increasing. Look back or rewind to reason number 2 for affects the acidity of things. So just kind of look at a trend across one period. If you look at a hydrogen attached to carbon compared to hydrogen attached to nitrogen, oxygen, and fluorine, the acidity increases from left to right here because the atom the hydrogen's attached to is becoming more and more electronegative. And so now, for example, as hydrogen fluoride acts as an acid, what it forms is a hydrogen ion and a fluoride ion. Okay? The more stable this anion is, the more acidic the original acid is. Now the other trend is as we go down a column, down a family, the acidity also increases. So it increases to the right and it increases going down. And that's because the bond strength between the hydrogen and the atom it's attached to decreases. Okay? Why do we want a weak bond to make it more acidic? It's easier to break. Okay? Remember, in order to act as an acid, it gives away that hydrogen ion. So the weaker this bond is, the more acidic it is. That could be short essay type questions that you might need to understand in your next test. So make sure you understand that. This one's a simple trend. If you're talking about an oxyacid or a ternary acid with 3 different atoms, the more oxygen, the more acidic. And basically, well, that's a bad word to use in this chapter. If you look at this first one, hydrochloric acid, when it acts as an acid, it dissociates into hydrogen ion and the chlorate anion. Okay? So remember, the more stable the anion, the more acidic the original compound or the original acid was. Okay? And so what that means is that as we add more oxygens, we're stabilizing this anion more and more, which makes sense because oxygen is electronegative and it's going to kind of share or disperse that negative charge of the anion. Now remember the K values. The larger K is the acid equilibrium constant, the more acidic that substance is. Okay, so you can see what happens to the acidity as we begin to add more and more oxygen. It gets stronger and stronger. Now, when we reach acids that are actually termed strong, in other words, they dissociate 100%, there is no Ka. If you have a strong acid or base that completely dissociates, there's no reverse reaction and therefore no equilibrium. And again, just to give you data to support the relationship between bond strength and acidity, here we're going down group 7A, okay, the halogens, and the bond strength is decreasing as we go down any column, okay. Basically, that's because the atom is getting larger and larger and larger, and larger atoms don't bond as tightly. And so look what happens to the acidity. As the bond strength decreases, the acidity increases. Virtually all the acid-base reactions we're going to be talking about are aqueous, are carried out in water. And so you need to get quite familiar with the generic reactions that occur with acids and bases. So if you have an acid, and I probably should have shown that as just HA, that's kind of the generic expression for an acid, and you put it in water, it's going to dissociate to give you the anion from the original acid and then a hydronium ion. Now bases, and again I'll just call that B. When you put them in water, remember they're going to abstract. Bases accept a proton. And so then what you're left with is, okay, the base that's protonated and then the leftover hydroxide from the water. So they're very different equations, so get familiar with writing both of them. And in both cases, though, the farther the equilibrium lies to the right, the larger the value of K. Remember, K is products over reactants. And so the larger K is, okay, the stronger the acid or base. Now there's a rather strange kind of correlation. It'll make sense in a minute, but the stronger the original acid, the weaker its conjugate base. Okay. Likewise, the stronger the original base, the weaker its conjugate acid. Nope. I think if we look at a chemical equation for acids and bases, we can see that relationship a bit better. So we have HCN, which is a weak acid. Remember, all acids that are not those 7 you need to memorize are considered weak. So here's a weak acid, and all weak acids and base exist in equilibrium. They don't 100% dissociate, and so like any acid, we get the hydronium ion and the anion left over. So now, if you remember what I just said in the last slide, if you start with a weak acid, its conjugate base is going to be stronger. The weaker the acid, the stronger the conjugate base. Okay, so they're oppositely linked. Same here. This is a weak base. You may have remembered me saying in class that amines, neutral compounds that contain nitrogen, are weak bases. So if you have a weak base to begin with, then you're going to have a stronger conjugate acid. So they're inversely related. And as just a reminder, strong acids and bases dissociate 100%, which means there is none of the original acid and base left. There's no reverse reaction and there's no equilibrium, so strong acids and bases do not have Kas or Kbs. All right, so a couple things I'm going to show you in this. First of all, again, the larger Ka is, the stronger the acid. So what is the strongest acid on this page? Okay, right here, chlorous acid. It's still not one of our 7 strong acids, or it wouldn't have a Ka. all right, but it's stronger than all of these. Let's see. So if I asked you a question, let's look at this reaction. This happens to be acetic acid, which is a weak acid. It's not one of the 7 strong ones. If I showed you that, told you it was a weak acid, and asked you if the acid equilibrium constant would be less than 1 or greater than 1, would you be able to answer that? I hope so by now, okay? Just remember that if you have an equilibrium constant that's less than 1, that means there's not very much product. In the case of an acid, it means weak acid, okay? Very weak acid. And if K is greater than 1, it's not one of the 7 strong ones, but it's a stronger acid than the weaker ones. Okay, I'd mentioned a couple slides ago, the weaker the original acid, the stronger its conjugate base. So look at the top. We actually have, let's see, the top 3 are literally strong acids that dissociate 100%. So all of the conjugate bases that go with those strong acids are very, very weak. In fact, they're such a weak conjugate base, almost considered to be negligible basicity. Now we get down to weak acids, but they get weaker and weaker as you go down. So let's look at the very, very weakest acids. In other words, these bottom 3 are not likely to give up a hydrogen ion at all. What that means then is that their conjugate acids are very, very strong conjugate acids. So just remember there's an inverse relationship in the acidity/basicity for acids and their conjugate bases. Alrighty, so we learned in the last lecture that pH equals minus log of the concentration of hydronium ion. It turns out that this little p literally means minus log of whatever the function we're looking at. So now we have something we call pK values, and that is simply the minus log of an equilibrium constant. Okay, so pKa is minus log of the Ka value, pKb is minus log of the Kb value, and just as with pH, the stronger the acid, the smaller the pKa. That'll make more sense, I think, as you do more calculations with it. All right, and a reminder again, pH is a measure of concentration. It is not a measure of the inherent strength of an acid or a base. If you have a pH of, let's say, 1, which is what your stomach acid is, by the way, that's quite acidic. But you cannot necessarily then say it's from a strong acid, because you can get a pH 1 from a weak acid if you dump a whole bunch of it in. So don't get pH mixed up with K. Those are the same, or those are not the same. K tells us about the inherent strength. pH tells us about concentration. All right, there is a relationship between Ka and Kb that I want you to understand, because you'll need to be converting from one to the other in some of these problems. So again, here's the generic chemical equation for an acid. Be very, very familiar with these. Here's the generic chemical equation for a base in water. And here are the generic expressions for the equilibrium constants for an acid and a base. Notice that Ka has hydronium ion concentration as a product, but Kb does not. Kb, instead of having hydronium ion in the numerator, has hydroxide ion. That's important because if you're dealing with a base and you have to do an ice table, what your X is going to represent is not the hydronium concentration, but hydroxide. So I'm just kind of planting the seed for now. All right, it turns out, and again, you don't have to go through this derivation, but it's always nice to provide them, that if you multiply Ka times Kb, you always get Kw. Remember that's the water equilibrium constant for water, which at room temperature is 1 times 10 to the minus 14. So why is this important? Well, that's important because let's say the problem gives you Kb and you don't want Kb, you want Ka. How would you find it? It would be 1 times 10 to the minus 14 divided by Kb. Okay, so you can interconvert between Kas and Kbs. Here's a sample problem. Ka for nitrous acid, and we're going to have to go back over the rules of naming acids. 4.6 times 10 to the minus 4th. Calculate Kb. So if you're calculating the Ka for nitrous acid, and they ask you for Kb, remember it's for the conjugate base of that original acid. So you need to know your conjugate acids and bases. Now, if you haven't already started to realize this chapter can get quite confusing, it can. I don't want you to get discouraged from that, but I do want to emphasize the importance of working the practice worksheets, perhaps listening to this lecture a couple of times, or reading the textbook. So the expression for Kb, since it's with a base, remember you combine a base with water, and you're going to get back the original acid, and then hydroxide will be left over. So Kb, as we said before, you can find it from Ka. It's just Kw divided by Ka. Please make sure that you know how to use the calculator you're going to use on your test correctly, because we're working with these very small exponents, and different calculators require that you enter the scientific notation in different ways. Please enter this problem right now into the calculator you're going to use on your test and make sure that you get this correct exponent as the answer. All right, here's one for you to try on your own. It's given Kb, calculate Ka. And here it is. I didn't necessarily tell you to write out the equation, but I just keep doing that because I want to emphasize the importance of knowing how to do that before we start ice tables. So Ka, of course, is 1 times 10 to the minus 14 divided by Kb, which the problem gave us, and therefore Ka is 5.6 times 10 to the minus 6. That is it for this second lecture, and the next lecture we'll be talking about ice tables for weak acids and bases.